values. If you notice, it also follows most to least acidic. And you could convert it to KB, rank them by how basic they are, and then kind of flip those numbers, but that might be a little confusing. So the easiest way would be to just use the Ka values. Okay. But make sure you have to rank acids and bases separately. So on a quiz, you might see a mix of things, not like this. I had all acids with a strong base titration here, but you probably won't see that on the quiz. You'll have a mix, in which case you need to rank them separately. And then Brandon asks to go over Ka of C and E. So Jacob, to answer your question as well, like I said, everything on the discussion worksheets, everything on this mock quiz is really reflective of the quizzes. So I would look at, I would think of all the questions as likely on being on the quiz. Okay, so to find the Ka of C here, all I would do is 1 times 10 to negative 14 power divided by their Kb value. Okay, so for C, the Kb value is 3.8 e negative 10, or times 10 to the negative power, negative 10 power. And so that will give you 2.63 e negative 5. Or it should, if I plugged it in right. Hopefully that makes sense, Brandon. And you'll do the same thing for E. Yeah. Okay. All right, so for the next question, we will be looking at ionic form again. Remember, we just covered that in the review session. So the first thing I want you to do is kind of make a number scale for all of them, with the pKa's being in the middle, right? So I'm going to pause the screen while I fill out all the pKa's. Oops. Okay, so what you're going to see, all you need to do at this point, I put all the pKa's in the middle. You're going to kind of mark where on this number scale is 7.4. Okay, so for the ethylamine, it'll be on the left side here. So the pH will be less than the pKa. For HF, it'll be greater. For the pyridine, it will be greater. For HClO, it will be lower a little bit. For alanine, it will be greater. Okay, and so by using the rules that we talked about, where bases are ionized before the pKa and acids are ionized after the pKa, we can answer this question. And so the only ones I see here that will be ionized is the first one and the second one. So any questions on this one?
Wait, so how do we know that they're ionized?
Yeah, so I can jump to the review session information. So so just to review, it's kind of a rule like when the pH is less than the pKa, then this will be the dominant form here. The dominant form will be the protonated form. When the pH is greater than the pKa, the ionic or deprotonated form will be dominant. And then for bases, the protonated form, which is going to be the ionic form for bases, will be dominant when the pH is less. pH is greater than the pKa, we'll have a dominant form of it being deprotonated. Okay, so again, to bring that all together, the protonated form will exist before the pKa. Okay, and so both the bases have a protonated and deprotonated form. The acids have a protonated and deprotonated form. that form will be always before the pKa. Okay, and here's the rule, as stated again. And then Ian, let me know what your question is.
Oh yeah, I just need to see that thing one more time if I can. When you're ready.
Oh, the quiz question.
Yes, ma'am.
Mm-hmm.
Only thing that confused me, I think we went a little bit quick on calculating the pKa, but it's normal. We would have done that during the actual quiz.
Yes.
Or,
yeah. So just for calculating the pKa, you'll just do for ethylamine. You have a Kb for ethylamine. It's a base, right? So the first thing I want you to do is convert this to Ka. Okay, and then all you need to do is negative log of the Ka value, and that will equal the pKa. Does that make sense?
yeah, that makes sense.
Yeah. So we're not dealing with any pKb's, right? We're only dealing with pKa's. So if you start out with a base, you want to always convert it to Ka, and then negative log of that, pKa. Okay. So here's a more conceptual question about thermochem. Okay, so let's break these down. The first one is saying delta H, or enthalpy, can predict spontaneity in standard conditions. What do you guys think? Yes or no? No, right. Okay, only delta G. Delta G can do that. Okay. So the next one is saying negative delta G can determine if a reaction is spontaneous under all conditions. Okay. So this is delta G, not delta G standard. What do you guys think? Yes or no? No. Yeah, because this does not account for the delta G under standard conditions. So under delta G, non-standard can only determine spontaneity under non-standard conditions. Okay. The next one is saying positive delta S of the universe means the reaction is spontaneous under all conditions. What do you guys think? Yes. Good. Okay. So if you know your rule, if you remember kind of your notes, I remember, so it should be delta S of the universe. And then you have delta G over here, and then they should kind of always have an opposite relationship, right? So if delta S of the universe is positive, delta G will be negative. This is negative, then this is positive. So both delta G and delta S of the universe can determine spontaneity. Okay, great. So then the next one is saying the value of delta G is 0 when a phase change occurs. So if you're paying attention in the review session, yeah, yes, true, good, okay. Perfect. The last one is saying delta H always has the same sign as delta S of the surroundings. What do you guys think? You can take a peek at your equation sheets if you'd like. Okay, good. They have opposite signs. Okay, good. Any questions on these before I move on? Can you explain B? Yeah, so negative delta G can determine if the reaction is spontaneous under all conditions except for standard conditions, right? Because this is not delta G standard. This is just delta G non-standard because it doesn't have the little degree. And so, yes, if that makes sense. If it said negative delta G non-standard and negative delta G standard, we can refer to all conditions. Does that kind of make sense? If not, that's okay. I can explain again. Yeah, okay. Standard and non-standard, yeah. So standard conditions is just kind of like a preset, like preset values for like certain conditions. I believe like pressure is one of them. and I believe in biology, concentration is one of them. So so yeah, so they're just kind of standard delta G. Standard has a preset of conditions, only under certain conditions that's predetermined by scientists. Yeah, they chose those conditions, and they said everything not in these perfect conditions that we chose will be just regular delta G, non-standard. Okay. Yes, Ian, yeah. Yeah, so make sure you know this because we'll be dealing a lot with delta G. Okay. So the next question I covered, we have a titration with this amount of ascorbic acid with this molarity, this concentration of LiOH. What is the pH at the first equivalence point? Okay, so basically what you can do here is just use the pKa's, right? So let me get my values, and then I'll jump to the next. I'll jump back to the screen. Just let me write these things down. Okay, so these are the pKa's. This is like pKa2 here, and this is pKa1. And so we'll find the average of those to get our final pH. Any questions on this one? Okay. So the next question is saying, we have a reaction at boiling point. Okay, boiling point. What does that mean? I think of a phase change. At this temperature, calculate delta G at this temperature. So the first thing we need to do is see what variables we have to use and then figure out what we're missing. So we know that at a phase change, delta G is 0. So that'll be equal to delta H minus temperature delta S. So we can kind of plug these in and see what we can find out. We know what delta H is right here. And then we know what the temperature is, which is right here. So let's solve for that. We don't know what delta S is. We're going to be solving for that so we can plug it in the next time when we're looking at a different temperature. Okay. So for delta S, you should get negative 0.203. So we're going to plug this number right back in. We're going to do delta G, because ultimately we're looking for delta G, right? Delta G equals negative 75.89. We're using the same enthalpy value minus 309 times negative 0.203. Jerry asks, if the temperature of the reaction is 309, then why are we saying that delta G is 0? We're first trying to solve, yes, like Ian said, we're first trying to solve for entropy here because we don't have that value, and then we can plug it in right over here, right? So yeah, the only reason I set this equation up was because we had enough information to solve for delta S. So yeah.
One part that, sorry, I got a question about this.
Yeah, go ahead.
One part that confuses me is that the change in entropy is the same when we do the state conversion. It's the same even when we're calculating for the delta G at a different temperature. I might be confused. Is it saying that we're actually getting to a boiling point with 309 K, or that we're just raising it to that temperature?
So that's a great question. We actually see this situation come up a lot, and so that is a good question. I wondered that myself, like why we have a boiling point here, and then that enthalpy and entropy translates to a different like the same enthalpy and entropy that we found here translate to a different temperature where it might not even be boiling. So that is a great question, and I can look further for you, but I'm not actually sure myself. But we will see this situation a lot, so try to recognize that if it does tell you a boiling point, it will still give you the same. You'll still be using the same delta H and the same delta S in the second part of the equation. I know it's a little confusing because they have different temperatures, and how is the reaction happening, the same reaction happening at different temperatures? But that is a great question, yeah.
So we just got to keep it like theoretically. We're getting to the boiling point at 3 and 9 K.
Yeah.
All right.
Kevin asks the units for delta S. Let me see really quick. Because we don't too often write out the units for entropy, but let me find out. Yeah, it'll be joules per Kelvin. Let me find my screen again. Okay, so yeah, the entropy will be joules per Kelvin. Okay, and so what you should get ultimately for delta G is negative 13.616. Okay. So the entropy remains constant. Yes, the entropy and the enthalpy remain constant. The only thing that changes is the temperature. Could you say that, and could you say the answer for number 4 again? Oh yes, sorry. Okay. So we can kind of jump to the next problem. So like we talked about earlier, for delta S of the reaction, we're going to be looking at things going from a more ordered state to a less ordered state to increase the entropy. Sorry, I'm getting a little distracted by the question in the chat. So just to finish those previous questions, for number 4 is just the average of both pKa's. Yes. How is H in kilojoules and S in joules? This probably is in kilojoules. Yeah, sorry, I just didn't write it out. Yeah, this probably should be in kilojoules, and especially how small it is. And then your final answer here will be in kilojoules per mole. Okay. Wait, don't we have to convert that delta S? I don't know what you mean by convert the delta S. There's no converting. This is that's all we need to do for the problem. We solve for delta S, and then yes, from joules to kilojoules. Don't worry, no. I just wrote the joules per Kelvin after I even solved the equation. Yeah, so don't worry about that. Just make sure you keep things consistent. Usually for this class, he makes things a little bit easier, at least right now. Later on, we'll do a little converting, but for right now, just kind of use the values you're given with and don't worry too much. But yeah, okay. He might ask you, you'll solve this question usually in kilojoules, and he maybe will ask you to write the answer in your quiz in joules. All you need to do is multiply by 1,000. Okay. So for number 6, we are just we're just going to be choosing reactions that go from a more ordered state to a less ordered state because we have entropy increasing. What kind of entropy? Entropy of the reaction. Okay. So here we will see that going from a gas to a solid, that will be decreasing entropy of the reaction. Going from a solid to a liquid, that'll be increasing. Going from a solid to a gas, also increasing. Gas to a liquid, that will be decreasing. And then liquid to a gas, again, increasing entropy. Okay, so any questions before I move on? Exactly, oh yeah. Okay. So we have a titration on a triphotic acid. Okay, you spill water on your lab book. So here's the important parts. These are the values that we have. We have pKa 3, and we have the first and second equivalence points. We don't have pKa 2. So let's kind of draw what that looks like. Okay, so basically to solve this problem, we're going to be using the average of the pKa's, and we're going to be using pKa2 as a variable we don't know. So I'll have pKa2 plus pKa3, which is 9.8, divided by 2 will equal the second pKa. Okay, so then once you solve for this, you should get 5.3. Okay. Right, we don't use 3.35. We don't need all the information in this problem. Okay. Is there a way he might ask this complicated, this question complicated on the quiz? Which question, Ian? Like number 7 or number 6? Yes. No, I mean, what we're reviewing will equip you with everything you need to know for the quiz, so don't worry. Okay. And so this problem, how many equivalences do you need to add to get this to reach the isoelectric point? Okay, so this is pretty straightforward. We start with a charge of +1, right? And so at every equivalence, we deprotonate 1. So if we were to draw the chart for this, and the initial charges, and then the charges, right, that change sequentially to the equivalences, we'll get something like this. And to get to the isoelectric point, that just means the charge is 0. And so all we need to do is get to the first equivalence point. So the answer here is 1 equivalence. Okay. Any questions on this one? How do we know it's +1? If we just take a look at the molecule, we count the charges, there's only 1 positive charge. So it's only going to be a +1 charge. Yeah, so there's nothing else we can protonate here. We're all good. Yeah. Will it show us the charges on the quiz? I mean, you might get a mix of things. You might get things fully protonated, already ready for you to go, or you might get situations where you need to protonate them yourself, like we've been practicing. And I think I have another question on here that looks at that, maybe. I think so. No, I don't think I do. I protonated them for you in this quiz. Okay. For number 9, you titrate this amount of aspartic acid. using pKa's from the previous question, and then you use 2.7 molar NaOH. Okay. How many liters of NaOH will be needed to reach a charge of negative 0.5? Okay. So if we kind of draw out what the titration will look like, aspartic acid has 3 pKa's, which means 3 places to deprotonate from. And it starts out with a +1 charge, like we just determined over here. And then if we were to continue writing the charges, we'll see a charge of negative 0.5 will be right here, right? Exactly at the halfway point. So this is, so the first thing we want to do is, let's see here. We recognize we need not 1, but 1.5 equivalences, right? Because this is, let me make this clear. I'll label the equivalences here. But here is 1.5 equivalences, okay? So we know we need 1.5 equivalences of base, okay. Okay, so the first thing I want to do is kind of find all the moles, all the liters, everything we're dealing with as much as I can. So first I'm going to find how many moles of weak acid I start with, so I can find out how many moles of base, a strong base, do I need to get 1.5 equivalences. Way that helps me count charge is by looking for O minus or NH without 4 bonds. Perfect, yeah. Okay. So first thing I'm going to do is find the moles of aspartic acid. So we'll do 0.679 times 1.6. Did I do that right? No. Yeah. Yeah. Okay, so this is how many moles we start out with. This is how many moles equal to 1 equivalence. Okay, so to get how many moles are equal to 1.5 equivalences, all we need to do is multiply that. Okay, so now that we know how many moles of NaOH we need to find out how many liters to use, right? 1 second. So all we need to do at this point is convert the moles to liters, and all we need to do with that is divide by the molarity, which is 2.7. Okay, any questions on this one? Okay. For number 10, we have this amount of carbonic acid titrated with LiOH. What is the pH at the end point? Okay, so this is kind of a multi-step problem, but it's not horrible. So the first thing to do is find out how many moles of carbonic acid you start out with, which if you just multiply those two numbers, you get 0.0375 moles of carbonic acid. And then we need to know what's at the end point, right? So as you know, the number of moles of weak acid you start with and a titration you'll end with at the very end as well. So this is the same amount of moles as of conjugate base, which I'm going to label A2 minus. And we need to know eventually what is the pH. And so we need to get our way around finding the molarity. The way we do that is dividing by volume, but what volume do we use? We need the total volume. And so we know that part of our total volume is our initial volume, but we need to find out what's that extra amount that we added, right? So we have to do a couple things. First, we need to find out number of moles of LiOH we used. And then the second would be to do moles over molarity to find liters. Okay, so the first step, what we do is we look at our number of moles, which is equal to 1 equivalence, right? So 0.0375 is equal to moles in 1 equivalence. And we know we reached the end point. And if we know anything about carbonic acid, we know it's a diprotic acid, right? And so what we need to do is multiply this number by 2, right? Because we need to go through 2 equivalence points to finish our titration. So when we multiply by 2, we'll get 0.075 moles. Okay, LiOH. Okay, so check, we know how many moles we need. All we need to do at this point is divide by the molarity, which is 0.45. This will give us our volume added because of the base. Okay, so I added that right over here. And we're going to finally find out what our concentration is of the conjugate base at the very end. So that should be 0.118 molar. Okay. And where do we go from here? All this is now is a weak base calculation. So we're going to do Kb2 equals the initial, which is 0.118, and x squared there. And we're going to do this regular or weak base calculation per normal. Okay, so I chose Kb2, not Ka, not Ka2, but Kb2, because we're at the very end of our titration and we're dealing with a conjugate base, no longer an acid, right? Okay. So once you do that entire weak base calculation, I can write it out if you guys need, but let me know. And I will just write out what you should get as your final answer. I can see if there's another molarity, but I have consistently gotten this one. So yeah, Modar, let me know. Do you have the same values as I put here for moles over molarity? Let me know. Okay. Well, let me know, and I can walk through the weak base calculation if you'd like. It's the same old, and you'll be finding the pOH with the OH concentration here, and converting that the pOH to pH. Okay, I can retry during the calculation. 1 second. I believe that it's because of rounding, Modar. Sorry, I don't know how to. I'm probably not pronouncing your name right, but it's probably a rounding error, or not an error, but it's due to rounding. I think they're close enough that you should get the same relative pH. Yeah, so I wouldn't worry too much about it. Okay. And then if anybody doesn't have any questions on the rest, I'll go to the last question of the day. All right. So this molecule will have a net charge at what pH? So the first thing you want to look at is what is our initial charge, right? So our initial charge here will be +3. Okay. And we need to get to a charge of +1. So if we draw our titration curve, we have 5 different pKa's here. So we're going to have 1, 2, 3, 4, 5 equivalence points. We start out with +3. We go down at every equivalence. So what's most important, we're looking for a charge of +1, and we have all the information we need. We can use those pKa's, right? So I'm going to use this pKa and this pKa there to calculate the equivalence points over here. So all I'm going to do, this will be pKa 2, this will be pKa 3. I'm going to take those, find the average, and then that'll be the answer. You should get numbers. You should get 7 when you do that. So you'll do, let's see here, 4.5 plus 9.5 divided by 2. Okay. For this one, which hydrogen would be removed first between the ones with pKa equals 11.7? I guess they would be removed at exactly the same time. But don't worry, that's not really relevant to this question. But they would be, yeah, they would be deprotonated at the same time. So that ultimately concludes that. I will stick around. I'm sure